My name is Megan Lewis, and I'm presenting on behalf of my team Pursuing Worldwide for our project, The Rope Pump. My team members consist of 2 civil engineering majors, Laura Clark and James Clary, and 2 mechanical engineering majors, myself and Mary Stanacci. Our advisor is Dr. Robert Ryan. This is our abstract. Our project was motivated by the inaccessibility of fresh drinking water in many countries around the world. There are about 800 million people worldwide that do not have access to fresh drinking water, and of these 800 million, approximately 3.4 million die per year as a result. Almost all of these deaths occur in developing countries. An efficient solution to this problem would be a rope pump design. A rope pump is a device that retrieves water from a well, which is typically hand dug. You operate it by turning a crank arm, which in turn rotates the flywheel or pulley wheel. Friction between the flywheel and the rope and pistons brings the rope around and down into the well, where it moves through a guide box. The guide box provides a smooth turning point as well as providing tension on the rope and stability for the system. The rope and pistons then move up the riser pipe, where the pistons trap water and expel it out the outlet pipe here. Some product specifications for our rope pump was that it would be $140 or less. This is because the market average cost for a rope pump is $160, so we wanted ours to be less money to provide a competitive edge. Our pumping head was determined to be 10 meters because this is maximum depth for a hand-dug well, and most wells on which rope pumps are installed are hand-dug. Our effective flow rate, which is the ideal flow rate minus the slip velocity of water moving past the pistons, is 45 liters per minute. And we determined this based off of a 3 liter per day average for people in developing countries, and to support the needs of the small community. And we also did not want people to spend an excessive amount of time at the pump to retrieve the water necessary for their family. Based off the ideal flow rate and the effective flow rate, we could calculate our volumetric efficiency to be 80.19%. Our energy exertion will be 50 watts due to the implementation of a 2-to-1 gear ratio. 50 watts is about the maximum power output of a child, and in places where rope pumps are installed, women and children are the primary operators of rope pumps, so we needed them to be able to easily retrieve the water. Turbidity the turbidity difference that our well will stir up will be less than 0.5 NTU. We made some overall progress since our last design review. We completed our prototype, we started testing, we figured out our area testing. And after our first rounds of testing, we found that no, our constraints were not met. So we had to go through a series of revisions of our design and our prototype in order to retest and meet our test results. When we revised our design for retesting, we focused on the flywheel, the piston placement, and the guide box. And we made these better and improved upon them in order to meet our design constraints. Our initial piston design was to be used from the sidewalls of a tire, where we would punch them out and assemble them into the conical shape as shown there. However, using the sidewalls of a car tire proves to be challenging because there is a steel wire mesh between the sidewalls of a tire. So when we tried to punch, no matter what method we used, as well as trying to grind down the outside, we ran into problems with making them easy to manufacture as well as cheap and uniform. So our solution was to use red rubber. Red rubber, due to the lack of wire mesh between them, was easy to manufacture, and we could create uniform conical shapes as you can see here, which would minimize the slippage. After a static analysis of the pistons, we determined that based off the weight of the water in the column and the force exerted on each piston, based off the overall surface area of the piston, each piston would sustain approximately 25 psi, which is significantly less than the 400 psi tensile strength of red rubber. Therefore, this is a viable solution to our problem. To make these pistons, we used punches of diameters 1 inch, 3/4 inch, and 1/2 inch, punched out washers from the red rubber, and assembled them with rubber cement, as you can see over here. We chose rubber cement because it is both non-toxic and easy to use. For the frame, we used parts of a recycled bicycle as well as black steel. From the ground to the horizontal bar at the top, our frame stands at 84 millimeters tall, and for the Y bars on the side, they are at a 33-degree angle for extra support and stability while testing. We use TIG welding to assemble our frame, which is a more complex form of welding, but it also provides a stronger weld for the purpose of our project. In order to meet one of our design constraints, our team had to go through a series of welding training for us. So we had welding training along with the help of Mike Samuels from the SAE department to assemble our frame and put it together. For our braking system and gear ratio, we use the 20-inch coaster bicycle, the Huffy Rocket, available for $49 from Walmart. The gear ratio comes from the sprocket gear at the pedal and the sprocket gear on the rear wheel. There are 36 teeth on the gear at the pedal and 18 teeth on the gear at the rear wheel, making it the 2-to-1 gear ratio that we initially talked about. The 2-to-1 gear ratio will effectively cut the power in half needed to operate our pump, because for every 1 revolution of the crank arm or pedal, the rear wheel or flywheel will spin twice. The braking system was an important design constraint of ours. We want the operators of our rope pump to be able to feel safe while using it. And when you operate a rope pump and you stop pumping, you have about 5 to 10 kilograms of water in the column. And the weight of the water in the column will pull the rope and pistons back down through the riser pipe, which in turn will cause the flywheel to spin backwards. And if the crank arm spins in tandem with the flywheel, it'll spin out of control and have the potential to cause someone some sort of bodily harm. So our braking system came from the coaster bicycle, because when you pedal backwards on a coaster bike, it brakes the pedal and the rear wheel in result. And this works because the driving sprocket has a brake cone on it. So when the backwards torque is applied, the brake shoes then press against the inside of the hub shell, which effectively stops the flywheel and the crank arm as a result from spinning. Our crank arm was made from black steel, which is bent at a 90-degree angle. We determined the radius of our crank arm based off the diameter of our flywheel by this equation of 1/2 times the diameter of the flywheel, plus 1 extra inch because the diameter of the steel piping we used was 1 inch. So our radius of our crank arm was 11 inches, which we then attached to the pedal on the bike for our crank arm. Our platform is needed in order to suspend the pump at an acceptable height. And it also needed to suspend it above an open area, so we had a straight drop for the rope and pistons as well as a straight rise for the riser pipe. It needed to be at 10 meters to achieve our pumping head, and it also needed to be stable and safe. As you can see here, we made our platform out of wood, and it suspended our rope pump with our frame, which you can see the triangle at the top, to the acceptable height, and we also used the railing of the stairway for extra stability and strength for our platform. Our riser pipe of a 30-foot or 10-meter pumping head, we chose to use PVC because it is cheap and readily available, and it can also withstand the pressures of the water moving up the column. There is a limit of 10 kilograms to be in the riser pipe at any given time based off the safety of those using the rope pump. So the 1.5-inch diameter pipe was not usable since it has 13.6 maximum weight of water in the column. Between the 1 and 1.25-inch diameter pipe, after running some calculations, we determined that the 1-inch was more effective because it provided better efficiency. Therefore, the diameter of a riser pipe will be 1 inch. However, after all this, we had some complications meeting our design constraints. These complications came with parts of our project that I will talk about now: the flywheel, the guide box, and the pistons and their placement. For the flywheel, typically for rope pumps, you use the sidewalls of a car tire, you cut the tread apart, and you secure the sidewalls of a car tire together with 6 spokes, and at the end of each spoke is a hub bracket. However, for the purpose of our project, we decided to go with a 20-inch diameter bicycle tire instead of a car tire. We sliced the tire down the middle and reversed the sides in order to create a V shape, and then we put the deflated tube of the tire between the two halves to create adequate spacing for the pistons between them. This created an width of about 2 inches for our flywheel. The bicycle, since it has a metal rim that goes around the outside, as well as additional spokes, provided more support for the wheel itself, as well as being more readily available in third world countries and developing countries as a recycled good and material in case the flywheel needs to be replaced, which would cut down on our maintenance costs. Complications that we had, which was one of the risks that we predicted, was that there would not be enough friction between the rope and the tire in order to pull it around while it's supporting the 5 to 10 kilograms of water in the riser pipe. So we came up with 2 solutions for this. The first was to space the pistons at 0.6 meters instead of 1 meter, because the pistons easily gripped on the tread of the tire, but where we had spanses of just rope over the flywheel, that's where the slippage occurred. And we also added bicycle tread between the 2 tire halves. As you can see here, this is our initial design with the deflated tube of the tire between them for adequate spacing. And in the after picture, we put tire tread between the 2 halves, which effectively increased the friction. For the pistons, our length of rope was 23 meters based off of this equation, and at pistons at 1 meter intervals, we had 23 pistons on our pump. However, based off the circumference of the flywheel, the rope is in contact with approximately half of the circumference at any given time. So in order to have 1 piston on the rope at any given time, we needed the distance between them to be half or a little bit less than half the circumference of our flywheel. So we had pistons spaced at 0.6 meter intervals. We also had a problem with these pistons after we glued them together with the rubber cement. When we tried to drill the holes through the pistons in order to put them on the rope, the torque from the drill was too much for the rubber cement to withstand, so the 3 pieces of our pistons came apart, as you can see here, after drilling. However, after performing static analysis on the individual pieces of the pistons, we determined that the rubber cement was not actually necessary, and we attached them to the rope then instead by tying a knot at the base and at the top of each piston to secure the 3 pieces in place. We also made an artificial well for testing. We needed this because we did not have access to any hand-dug wells in order to test our project. We used two 55-gallon drums, which we stacked on top of each other, as seen here, in order to provide extra volume to prevent the need for constant refilling during testing. We had difficulty creating a watertight seal between the two drums, however. We initially just went with putting caulking on the outside and the inside of the seal, but we still had sufficient leakage when it filled past the seam. In order to overcome this, we put duct tape around the outside as well as a rubberizing spray, which filled most of the leaks. So once we filled it past the seam, we had a little bit of water trickling out of it, but nothing detrimental to our project. So to keep the testing area dry and safe, we put a baby pool underneath our well in order to catch any of the extra spills. The guide box is, as I said before, is made to guide the rope and pistons through a smooth turning point, as well as provide stability and tension on the rope for the system. Our design is a concrete casing with a glass bottle insert. As you can see here, the outside is concrete, and then we have inlet and outlet pipes, where they go down around the glass bottle right here, and then provide a smooth turning point. This, what you see right here, is a 4-inch diameter PVC, and that provides water flow through the system and also keeps the space for the rope and pistons to move successfully through. Complications with our initial guide box that we made was it was way too large. It was very heavy and hard to place into our two 55-gallon drums. So we needed to make it smaller in order to make it able to be placed in 10-meter deep well. The pipes were also too far apart, making the turning point too horizontal, so the rope and pistons got stuck. As you can see in the before picture, with the more horizontal turning point and the larger guide box, and afterwards, we have the smaller volume compared to the broken apart shell of our previous guide box. For testing, we had to test for flow rate, energy exertion, turbidity, and structural integrity. We tested flow rate using two different ways. We use a cyclometer to measure the ideal flow rate by taking a cyclometer for a bicycle and attaching it to the flywheel. This would measure the velocity of the flywheel with respect to the RPM, and multiplying by the cross-sectional area of the pipe would give you the ideal flow rate. Measuring the displacement, we also measured the displacement per minute that our pump generated. To do this, we timed for certain intervals, and then we took the amount of water pumped during that interval and we weighed it, and then we converted that weight into the respective volume, giving us our effective flow rate. The ideal flow rate and effective flow rate were then used to find the volumetric efficiency. The energy exertion, we collected data from different volunteers, and we also calculated the power from the RPM of the crank arm. For our collection of data, we were initially going to use females and children in order to pump our pump, but based off the height of the platform during testing, this was not viable because it was not safe for them to be standing on any platforms and reaching that far. So we collected data from that. For turbidity, we used clay from the construction site outside the engineering building and a spectrophotometer to test the turbidity. And for structural analysis, we did a static analysis on the frame and pistons to determine that it would indeed support the weight allowed. For our average flow data, at a duration of 32.26 seconds, we got 36.18 kilograms of water. This translates into an effective flow rate of 56.65 liters per minute and a volumetric efficiency of 70.27%. For our average power data, the average speed of the crank arm was 4 kilometers per hour and the average speed of the flywheel was 8.2 kilometers per hour. After converting this into RPM and calculating the power of each, we determined that the power at the flywheel was 104.74 watts, but the power at the crank arm was 47.47 watts, so we effectively cut the power in half required to operate our pump. If you compare our product test results to our initial product specifications, you can see that at $138.03, we were less than the costs that we initially stated. Our pumping head we achieved to be 10 meters based off of our platform, and our average effective flow rate was 56.56 liters, which was more than our design constraint of 45, so we achieved that one. At an average volumetric efficiency of 70.27%, it was about 10% less than we initially planned, but due to the fact that our power and our average effective flow rate were still meeting our design constraints, it was not an issue, as this was not one of our constraints. Our average exertion energy, as told before, was 47.27 watts. For turbidity, however, we did not have sufficient test results. We didn't let the sediment settle in the well long enough before we tested. And we also, when we were testing, we took samples primarily from the outlet pipe as opposed to the outlet pipe and the well for each set and comparing the two. So we have to retest to get correct results for turbidity. However, based off of the design of our guide box and based off our calculations, we still hope to achieve the less than 0.5 NTU difference. This is our cost analysis. As you can see, we have $138.03 as our estimated cost of materials, which meets our constraints. And for our project schedule, we have to build the shroud for exposure limitation, we also have to retest, and we have to edit and finalize our design document. Any questions? And do I have time for a video? Video is 1 minute.
Sure.
And that, what you saw there was when our guide box wasn't right and the rope and pistons got stuck when they went through the guide box. And this was before we fixed the rope and pistons, so we had a lot of slippage. So our flow rate was not what we achieved at the end, as you see here. And this was after we fixed the slipping problem at the flywheel. We got a much better flow rate. And there you can see the rope and pistons moving into the guide box. Any questions?
Yeah, I was wondering, we had a hand crank in our project too. How did you come up with the length needed for the?
Well, we had that equation, which was half the diameter of the flywheel plus 1 extra inch for the radius. But we also compared it to the radius of the arm of a woman and child because it had to be a good radius for them to be able to pump it. And since they were about the same, and since ours was a short enough radius that it would easily be used to base it off both of those constraints.
So in regards to that crank arm, why is it important to relate, given the gears that you have on this, why is it important to relate the crank arm radius with the flywheel diameter, or the flywheel radius?
I'm not 100% sure. I can get back to you on that though. That equation was one of the ones that we got from different handbooks on rope pumps, and that's the typical equation that they use. And it also correlates to the fact that the diameter of the flywheel is it's a lot larger, so the rope has more room to travel over it, and the diameter of the crank arm has to be shorter in order to effectively be able to crank it, because if you had a 20-inch diameter crank, you'd be cranking around in a pretty big circle as opposed to half that distance. I'm not 100% sure how the two correlate, but that was one of the equations that we got off like rope pump handbook, so I can look into that and get back to you.
I think the equation was that the radius of the crank arm was equal to half the diameter.
Half the diameter plus 1 extra inch, yeah.
So the diameter of the crank arm is in fact the diameter of the circle that the crank arm makes is the same as the flywheel.
Yeah.
Essentially.
Yeah, essentially. Plus 1 extra inch because of the radius of piping you use.
Other questions? In terms of the 10 kilogram weight limit, this is the weight of the water inside the riser pipe.
Yes.
Why is that a concern?
It's a concern because when you're standing over a pump and you're cranking to get that much water out, it takes a lot of strength and a lot of extra power for the 10 kilograms to rise, as well as having a lot more weight in the column should you stop pumping. It would be a lot more force pulling backwards on the wheel to make it spin backwards a lot faster, which in turn would be detrimental if you didn't have an automatic locking gear like ours. But as far as just like the weight goes, since we do have the gear ratio, it's just specifically because if you're pumping it at 10 meters high, pulling 10 kilograms or more up a 10 meter pumping head or higher, it's just going to be a lot of energy exertion and be pretty hard to retrieve your water. So you want to make it an easy solution for people to get fresh water.
One last question, the angles on your frame, you said they were 33 degrees?
Yes.
Why did you design this for a 33 degree and not 30?
We didn't design specifically for the angle. What we did was we wanted them to be a certain width apart at the bottom in order to provide extra stability, because if you look at some rope pump designs, like if you look at the team from last year, they have a very small angle, and at that point if you get into cranking it and if you're pulling a lot of water weight, your frame can rock and it can be unstable. So we wanted it to be a substantial width on the floor in order to be stable. So we chose 2.5 feet across for the distance on the bottom, and then with the respective height that we chose, the angles ended up being 33 degrees after you make the legs symmetrical.
Okay. All right. Any other questions? All right, thank you very much.